lovely people. How's everybody doing? Hi, Jalaj. Hi, Namrata. Hi, Takia. Takia, you're going to probably have to give me a bit of a pronunciation guide for that one, if you wouldn't mind. Hi, Steffi. Hello, Resurrection Stone. Very strange name you have there. Why are you the Resurrection Stone? Is that a Deathly Hallows reference or some other kind of fandom reference? Hey, Raoul. How's everybody doing today? Wishing it was sunnier? I am wishing it was sunnier. We'll get started in a little while, just sort of wait for a few more people to arrive. The plan is today to be doing ideal gases, and I suppose I could just introduce myself while we're here. So I'm Georgia, and then today the idea is that we're going to be sort of, if you haven't been to these before, that essentially I will sort of show you an exam question, you have a go at it, I give you a little bit of time to do that, and then I will sort of talk through it and answer any questions that you might have. You love calculations? That is a good thing, Jalaj. Did I get your email? When was that? Possibly. I'm a bit frazzled at the moment. I've got a lot of balls in the air, so I'm getting a bit frazzled with my emails. But if you sent one, I probably got it. Oh no, I did. I remember. Yes, I did. Sorry, my brain is a bit like a full bucket, and all of the information keeps sloshing out of it. But yes, I'm glad I said it fine, Takia. Let's get started. Why not? Hi, Georgia. Oh, hello, other Georgia. Maybe I should call you contemporary Georgia, and I shall be antique Georgia, or something like that. Ooh, that's good. Okay, all right. So ideal gas stuff. Hey, Manda. Georgia Jr. Well, I don't know the sort of relative ages. Not everybody here is sort of at sixth form, so I will assume nothing about age. Okay, cool. So as usual, at the end, there will be a discount code that just sort of is our, what is it called? A carrot, the carrot that we hold in front of you for sort of sticking around and hearing about our platform at the end when I sort of ramble about it. But otherwise, let's just sort of get on with it. So the first question says 100 centimeters cubed of hydrogen is mixed with 25 centimeters cubed of oxygen at a temperature of 150 degrees Celsius. And these gases react as shown in the equation below. So we've got 2 moles of hydrogen reacting with 1 mole of oxygen, making 2 moles of water. And it says that the total volume of gas, present at the end of the reaction is, and then we have some options. So go for it. Tell me, is it A, B, C, or D? And yes, Namrata, the equation is PV equals nRT. You are correct. When will I cover topic 5, moles and hard calculation stuff? So to some extent, this is moles stuff. There's plenty of molesy stuff in here. We were supposed to do moles the week I got sick. So I'll probably pop on another YouTube class in the schedule for moles and stuff, but we will get to that. So I want you guys to think really carefully about this one, because there's an answer that feels like the right one that's quite obvious, obvious in inverted commas, but is actually the wrong one. So just be a little bit careful. Think about what happens at the end of the reaction. That's a really good question, Andre. You know what? I'm not entirely sure. I'd have to research that a little bit. But if you drop us an email, if you drop an email at hello@snapprovides.co.uk, then we might be able to give you a little bit of advice there. But I just don't know off the top of my head. I'd have to like compare the specs. Is this the first section of the question of the live stream? Yes, it is. You have not missed one much. So I'm going to answer the question because we've had plenty of people answer. So lots of you said C, and I know why you said C. I know that you thought, okay, so we had 100 centimeters cubed of hydrogen and 25 centimeters cubed of oxygen, so therefore we add them together and it gets 125, but that's actually the wrong answer. That's not how it works. The right answer is B, 100 centimeters cubed. And that's because it's at the end of the reaction. So this isn't a reversible reaction. It just is, it has one direction. And at the end of the reaction, we will have water rather than, and it's still gaseous water. But we, at this point, to figure out the volume, we need to be looking at the molar ratios, right? So if we have 2 moles of hydrogen producing 2 moles of water, then it's the hydrogen's volume that we kind of want to look at, right? And there's 100 centimeters cubed of hydrogen. And as there's a 1-to-1 ratio between hydrogen and water, that means that at the end of the reaction, we should have 100 centimeters cubed of the volume of the water vapor. Does that make sense? So it should be B. Does anyone have any questions in terms of that? Or are we good? How does the volume of oxygen seem to disappear? It doesn't disappear, Kang. So the reaction, well, the oxygen is now part of the water, right? You've reacted hydrogen and oxygen together. So they're sort of now one molecule. Does that make sense? Is this about limiting factors? No, this is not about limiting factors. It's not about limiting factors at all because we haven't been told the sort of pressure. It's all about the molar ratios. So let's ignore the fact that it's hydrogen and oxygen and water. I'm just going to say A and B and C. So we react 2 moles of A and 1 mole of B to get 2 moles of C. 2 moles of A is going to take up a lot of space compared to 1 mole of B. So if you have sort of double the number of moles of something in gaseous form, it's likely to take up more space, right? So what we're trying to think about is how much space does our product take up? So there's 2 moles of our product. And we know that 2 moles takes up 100 centimeters cubed because we've been told that 100 centimeters cubed of hydrogen takes up that 2 moles of hydrogen take up 100 centimeters cubed. So the fact that we have 2 moles of it in our product tells us that should take up about the same space as the 2 moles of hydrogen, molar ratios wise. Does that make more sense? So it's not that we're ignoring oxygen, it's just that the oxygen's been reacted already. We're just using the hydrogen's value to tell us that 2 moles, sort of molar ratio wise, should take up about 100 centimeters cubed. Does anyone have any more questions? Yes, exactly. They're homogeneous. It's a homogeneous reaction. Everything's a gas. All right, I'm going to move forwards because so you always look at the number of moles. Yes, if you're trying to sort of compare volumes, remember that they've come together. So this isn't just about moles. It's about the fact that you've got your hydrogen and your oxygen bonding together. So this means that for every sort of 3 moles of reactant, there's only 2 moles of product. And you guys know, or at least you should know, that pressure-wise, the size of the molecule doesn't really make any difference, right? Like having 3 sort of atoms in a molecule compared to 2 in a gas is not going to change the volume because gases are so spread apart. So it's also about recognizing the fact that it's all about how many gaseous molecules you have, not the size of the gaseous molecule. So I'm gonna move forwards from this one. Okay, so the next question. What happens if there's only 1 mole of product at the end? Then it would take up less space. So theoretically, the steam is more dense than the hydrogen gas. So you don't use density for gases. Density is for solids. You use pressure for gases. And not really, because when we model gases, we kind of just assume that they're all a hard sphere of about the same size. So the modeling for gases sort of doesn't really, you don't really think about size too much, at least not at this sort of level. So gases are always pressure, not density. Okay, moving forwards. Sodium nitrate decomposes on heating. What is the maximum volume of oxygen measured in decimeters cubed at room temperature and pressure, which could be obtained by heating 0.5 moles of sodium nitrate? And our formula is we've got we've got NaNO3, 2 moles of that, producing NaNO2, 2 moles of that, and some oxygen. So I'm going to give you guys a little bit of time to do that. Cool. So lots of you are saying B, and those of you saying B are beautifully correct. So if you were confused, you could have used the ideal gas formula, but that would have been really long. So you could have used PV equals nRT and gone about it the long way round, but there's an approximation that you can use when things are at room temperature and pressure. So that approximation, as Raoul has just said, is you times by 24. So its volume is equal to 24 times the number of moles. So this is just, if you have everything at room temperature and pressure, you've sort of, the pressure's already been put in the formula, the ideal gas constant has already been put in the formula, the temperature's already been put in the formula, and all of those together give you 24. So this is the approximation you want to use, and it sort of reminded you of that approximation here, just in case you forgot, which is very nice. So what you're really doing is the volume is equal to 24 times N, and you've been told that there are 0.5 moles of sodium nitrate. So if this is our sodium nitrate, so that would be, the volume would be equal to 24 times the 0.5, which gives us a value of 12. But as you can see, there's a 2-to-1 ratio. You have 2 moles of sodium nitrate to every 1 mole of oxygen. So that's half the volume of oxygen. So we divide that by 2, and that gives us 6 decimeters cubed of oxygen. Does anyone have any questions? Before I move on. Everybody understand the approximation and the... Yeah, we good? Why do they teach you the long way? You have to be able to use the long way if it's not room temperature and pressure. If it's a different temperature and a different pressure, then you need to use PV equals nRT. You can only use this at room temperature and pressure. So the question will either tell you that by saying that it's at 100 kilopascals and 25 degrees Celsius or 298 Kelvin, or it will just say at RTP. room temperature and pressure. So room temperature is 25 degrees Celsius, which is 298 Kelvin. Cool. Let's move forwards then. So the next question is a little bit longer. It's a calculation, but it's still a reasonably nice one. So this question says, a student heats 5.29 grams of tin nitrate. Oh, that's not tin. Is that strontium? Strontium nitrate, and collects the gas at room temperature and pressure. So that's our RTP. So again, we're at our room temperature and pressure. And then we have our nice formula, so we have 2 moles of strontium nitrate in its solid state, and then we have strontium oxide as a product, and we also have nitrogen dioxide as a product and oxygen. So we've got 2 gases there and a solid for our products. And it says calculate the volume of gas in decimeters cubed attained by the student at RTP. So again, that's room temperature and pressure. So the molar mass, and we've also been given the molar mass, so they're being super nice to us there, and telling us that the molar mass of strontium nitrate is 211.6 grams per mole. So again, we can use our approximation. What's our approximation when we're when we're at room temperature and pressure? So we could use PV equals nRT, but that would be long. What's the formula for the approximation? Anyone? It was on the last page. Yeah. So if you remember the formula for the approximation, it's going to make your life a lot easier. If you forget it, it's not the end of the world. You can still use PV equals nRT. But remembering this is it just makes life easier, doesn't it? Then you don't have to shove everything in the formula. Okay, so we know that we can figure out our volume, which is what you want. It said calculate the volume by doing this. So the unknown value is N, is our number of moles. So what number of moles are we looking for? So Namrata said the moles equals 5.29 divided by 211.6. What number of moles would that give us? And what number of moles are we looking for? Any ideas? Yeah, you're looking for the moles of the gases, so of NO2 and oxygen. I'm going to leave it there. I'm going to let you guys just finish the question. Give you a couple of minutes to have a go at that, and then I will go through it in full. Those were your clues, people. Oops. How do you know when to use V equals 24 times N? That's the PV equals nRT formula with room temperature and pressure and the ideal gas constant already shoved in. So if you're at room temperature and pressure, so if you're at 25 degrees Celsius / 298 Kelvin, and just sort of in a normal room, so room pressure, then you can use that approximation. I'm going to give you another few seconds to finish off, and then I will go through it. some good answers in there. Most of you seem to be getting the right answer, so that's a good sign. All right, so the thing it's asking us for is the volume of the gas. So that's going to be our oxygen and our nitrogen dioxide, right? But the only information we have is how much of our reactant we've heated, which means that we first are going to need to figure out a number of moles of our reactant, and then we can use that to figure out the number of moles of gas and therefore the volume. So my number of moles of my reactant, so my strontium nitrate, is going to be the mass divided by the molar mass. And very nicely, they've given us the molar mass and the mass. So we've got 5.29 divided by 211.6 grams. And that should give you 0.0250. And that's for our three significant figures. So at that point, we want to figure out what the number of moles of our gas is. And that our gases are our NO2 and our oxygen. So that's what we're working out, the number of moles of those. And we're going to do that with our molar ratios, right? So in terms of molar ratio, for every 2 moles of the reactant, we get 5 moles of our product, because there are 4 moles of the NO2 and there's 1 mole of the oxygen. So every 2 moles of strontium nitrate, we get 5 moles of gas, which means that to work out the number of moles of the gas, I'm going to take my number of moles of my reactant, and I'm going to times it by 5 and divide by 2, right? So I'm dividing by 2 to get down to like what it would be if there were 1 mole, and then I'm timesing by 5 to sort of make up to the 5 moles of gas in the products. So that should give us 0.0625. How do you know that it's already in decimeters cubed? Because that's the standard unit for volume. So the ideal gas formula is in decimeters cubed, at least in the approximation. So in this approximation, we're in decimeters cubed. In the normal ideal gas formula, we're in meters cubed, but in the approximation, we're in decimeters. So that should be fine. Yeah. Okay, so we're at our number of moles of gas. So all we need to do is figure out our volume of gas, which is 24. This is using our approximation, which is 24 times 0.0625, which should give you 1.5 decimeters cubed. Why do you include oxygen in this calculation? Because there's 1 mole of oxygen. So remember, when we're thinking about how much volume of gas there is, it's all about how many moles of gas there are, rather than the size of the molecules. So you have to include every sort of molar value, and they're both gases. Cool. So I'm just going to make sure I didn't miss any questions. Isn't it 150 because the equation gives you meters cubed? Just in case you didn't hear what I said before. So remember that the normal ideal gas equation is you're right, the volume is in meters cubed, but this approximation uses decimeters cubed. So that's an important thing to remember. Any questions before I move on? You thought there were 2 moles of strontium nitrate. There are 2 moles of strontium nitrate. So strontium nitrate, there are 2 moles of it for every 5 moles of gas, which is why when we worked out the number of moles of the gases, we timesed by 5/2. Yeah, so yes, Kang. So I could have put just M for molar mass there. Molar mass and molecular mass are basically the same thing. So you can kind of, in formulas, you can kind of use them interchangeably. You don't understand the second step. So remember, guys, if if you don't understand something, this goes for any teacher ever. So when you're at uni, when you're at school, when you're at sixth form, saying I don't understand, I can't sort of like guess where that is. So you kind of have to tell me like, I get this bit, but here is where I got confused. Being able to form your questions well is like a really important part of the learning. So what does the 5/2 represent? So that's when we're sort of making up for our molar ratios. So here we have 5 moles of the gas in the products compared to 2 moles of the solid. So we, at the beginning, we worked out our number of moles of the solid of our strontium nitrate, and we're trying to work out how many moles of gas that would have produced. So we sort of do it like a fraction. So we're dividing by 2 to get down to sort of like how many, what the volume, how many moles there would be for like 1 mole, and then we times by 5 to get back up to 5. So that would be 5/2. So the 5/2 is to get from 2 moles to the 5 moles of gas. That's why we're timesing the moles by 5/2, to deal with the fact that we've got two moles of strontium nitrate producing 5 moles of gas. And that 5 comes from the 4 moles of nitrogen dioxide plus the 1 mole of oxygen. I hope that makes sense. Yeah, the 5/2 is the ratio, the molar ratio calculation. What equation did I use in step 1? I used moles, I used mass divided by molecular mass to get the number of moles. I'm going to move forwards, lovely people. There will be more molar ratios. So if molar ratios are a bit confusing to you, they are coming up in the next few questions anyway. So you should possibly get some practice of them there. Okay, so this question is the reason why this thing was called ideal gases and other calculations, because most of the time your ideal gas questions are going to come within other amounts of substance questions. So that is the reason that it's and other. So this first bit's not necessarily that ideal gassy, but it moves on to an ideal gas bit. Why did I use a 0.025 times 5/2? So as I said just now, never mind. Did you understand what I said before? So we could only work out the number of moles of the reactant from the information in the question. So we worked out the number of moles of the reactant, and then we did the divide by 2, so the bottom of the fraction, to get down to what that would be for 1 mole, molar ratio wise. And then the top of the fraction, the 5, comes from the fact that we have 5 moles of gas in the product. So you divide by 2 and then times by 5. So that's the same as saying the fraction 5/2. So by timesing the moles of the reactant by 5/2, we get the moles of gas in the product. I hope that makes sense. Try to, if that doesn't, try to sort of like think about it after we've sort of done the class, and maybe it just needs a bit of time to sort of settle in. Cool. All right. So this question says, some airbags in cars contain sodium azide, so NaN3. Sodium azide is made by reacting the dinitrogen monoxide gas with sodium amide, so that is NaNH2, as shown by the equation below. So we've got NaNH2, 2 moles of it, reacting with nitrogen dioxide, and that gives us our sodium azide, NaN3, and then also some sodium hydroxide and some ammonia. And it said calculate the mass of sodium amide. Need to obtain 550 grams of sodium azide, assuming that there is a 95% yield of sodium azide. Give your answer to 3 significant figures. So I'm going to give you a little bit of time to have a go at this one. It's a 5-mark question, so there's quite a lot to do. Again, this is sort of like just a general moles question that's going to lead to an ideal gas. Deal with the yield at the end of the question. You could deal with it at the beginning, or you could deal with it at the end. It's up to you. So have a go at this one. And remember to deal with the yield, and you're looking for the mass of sodium amide. So that's the reactant needed to obtain 550 grams of the sodium azide, the product. I'm Well done, speedy Numer. I will let you know if you're right in a few minutes. You're going to have to assign that one yourself, Namrata. The question won't tell you what it is for the formula. Try to sort of work it out by what by the wording of the question. So well done, everybody that's had a go already. I'm going to give you guys just a little bit more time to have a go at this. If you're stuck, you only have to be stuck for a little longer, and then I will go through it. Okay, all right, I'm going to go for it because I've got quite a few answers in there. Some of them a bit dodgy, some of them correct. So I'm going to get started. So I've got lots of people have had a little bit of trouble with the interpretation of what this sort of like the yield bit means. And I think that's why it's important to do questions like this, to sort of get practice interpreting questions yourself, and picking out the sort of what this means in terms of what you've learned. So it tells us that we want to calculate the mass of sodium amide, so this thing, needed to obtain the sodium azide, needed to obtain 550 grams, assuming there's a 95% yield. So if there's a 95% yield, we're going to need sort of theoretically to make more than the 550 grams, right? Because we're only going to get 950. So to sort of figure out how much we should aim for, that's going to be sort of like the 100% yield. So 550 is at 95% yield, because that's the yield we're going to get. So we need to sort of like calculate our amount of reactants to make the 100% yield. And the way that we do that is we do 550 times 100 over 95. So if you've forgotten how to do stuff like that, that is a GCSE maths topic. A GCSE maths topic that you can sort of have a look at, and it should be called either normal percentages or reverse percentages. So if you need to have a bit of a revise of that, remember anything from GCSE maths can come up in your A-level, chemistry A-level exam. So if you need to revise that topic, go ahead and do that. Usually the question for GCSE maths is something along the lines of, in a sale, a t-shirt costs £16 and that was at 20% off. What's the original price? And this is sort of basically that kind of question. So the amount we should be aiming for should be 579 grams. So that 579 grams is sort of like our 100% yield mass. Like if we sort of like theoretically, we made what we thought we were going to make, that's how much we need to make. At this point, we're looking for the mass of sodium amide, but we just know how much we want to obtain. So I'm going to use my molar ratio. So I need my number of moles of sodium azide that I would be producing if I had 579 grams. So that is the formula when I'm using my mass divided by my molar mass or molecular mass. So I should be doing my mass, which is 579, divided by my molar mass, and my molar mass for sodium azide should be 65. So I should be doing 579 divided by 65, which is equal to 8.91. So that's my number of moles that I need that I will be producing of my sodium azide theoretically. So I'm getting lots of questions about why you can't do percentage increase rather than, so remember that if you were to do it like that, what you would be assuming, Sarge, by increasing it by 5%, is you'd be assuming that the 550 grams is the 100% value, and that the your value is actually your 105% value. So by doing it that way, you're not assigning the 550 grams at 95%. You're assigning it at 100. So percentage increase, working that out is not the same as working out sort of reverse percentages. So be careful about that. Cool. So Kang keeps saying you can use the equation to figure it out. Yes, the equation rearranged is doing exactly the same thing as this. So yes. Okay, so we have our number of moles of sodium azide, which means that we can use our molar ratios to figure out how many moles we're going to need to put in of our sodium amide. So our sodium amide, NaNH2, has a 2-to-1 ratio with our sodium azide. So we have 2 moles of our sodium amide compared to every 1 mole of sodium azide we create, which means that we're going to need to times that value by 2. Different methods are a really good idea. So then people can use the one they find easier. So yeah, no problem with doing that. Cool. So our number of moles of sodium amide is then 17.82. So we have our number of moles of sodium amide that we're going to need to put in to get that mass of sodium azide. So at this point, it's just sort of like the simple using the equation to figure out what the mass is. So our formula for mass coming from moles is, of course, our number of moles times our molar mass again, or molecular mass, whichever you want to use, which should give us the sum 17.82 times 39, which is equal to 695 grams to 3 significant figures. Does anyone have any questions? Yeah, because quite a few of you got that. Some of you, I think it was the sort of percentage yield thing that threw people off. But that should have been what you got. No, we good? Awesome. All right then, I'm going to move forwards to the second part of this question, which is our last question. Hopefully that means I'm kind of running on time-ish, which basically never happens. Cool. All right, so the last part of this question says, if a car is involved in a serious collision, then the sodium azide decomposes to form sodium and nitrogen, as shown in the equation. So here we've got our sodium azide decomposing, and this is what happens in our airbag. So nitrogen produced then inflates the airbag to a volume of 7.5 times 10 to the minus 2 meters cubed at a pressure of 150 kilopascals and temperature of 35 degrees Celsius. And what we want to do is calculate the minimum mass of sodium azide that we must decompose, and we've been given our ideal gas constant, which I think this question is really cool, right? Because now you guys know how airbags work, and just from an exam question. Azide is pronounced azide. Me make a 2. Okay, so we've got, we're trying to figure out the mass of sodium azide that must decompose to produce a specific volume of gas. And the only gas we have here is our nitrogen. So which formula are we going to be using to figure out the sort of the mass of sodium azide that we need to produce that volume of gas? So these, I'm just going to sort of set you up with your formulas and then let you go ahead. So which formula are we going to be using for this? Yeah, we're going to be using our normal ideal gas formula, so PV equals nRT, and because we want mass, we're eventually going to be using our number of moles is equal to, or really we want mass, so we're going to be using our mass is equal to number of moles times molar mass. So I'm going to give you those, and yes, so Mitzi's asking me how to convert degrees into Kelvin, which is a good point, but I'm not going to tell you. You're either going to remember or you're going to Google it, but I'm going to let you guys have a go. So remember, it's really important to remember which units PV equals nRT uses, because otherwise your answer will be wrong. So make sure you try to remember that. Is the gas constant always given in the question? Sometimes you have to get it from the data booklet, but they don't expect you to remember it. So it's either going to be in the question or you'll have to look in your data sheet, but it's going to be there. And remember the correct number of significant figures. Got another couple of minutes. Got like 30 seconds. Yeah, so 3 significant figures in general is the standard for A-level. All right, I'm going to go for it. I'm going to do and explain. Okay, so our formula that we have is not in the right sort of order for our use, because we're going to be trying to find the mass, which means we need the moles, so we need to rearrange for mass, which most of you sort of seem to be fine with. So the formula we're actually going to be using is number of moles is equal to PV, and that V should be big, over RT. And as you guys should see, your PV equals nRT. First of all, your pressure must be in pascals, not kilopascals, and your temperature must be in Kelvin, not degrees Celsius. So the first thing I'm going to do is identify that 35 degrees Celsius is the same as 308 Kelvin. So all I did was add 273, and my 150 kilopascals I'm just going to add 3 zeros to get to pascals, times by 1,000. So it should be 150,000 pascals. So at this point, we're ready to shove things in formula. Do we need to convert meters cubed to decimeters cubed? No. Your ideal gas formula is in meters cubed. It's just the approximation that we used earlier that's in decimeters. Okay, so literally just going to shove things in. So my number of moles, and remember that the number of moles that you're working out is going to be your gaseous number of moles. It's the ideal gas formula. So the only thing you can be working out with these values is the number of moles of the nitrogen gas. So my number of moles of nitrogen gas is equal to my pressure, which is 150,000 pascals, times my volume, which is my 7.5 times 10 to the minus 2 meters cubed, which is the correct unit for the ideal gas formula. And it has to be divided by our ideal gas constant, which is 8.31, times the temperature in Kelvin, which is 308. So that should give you 4.40 moles. So that's keeping us to 3 significant figures. Yeah, so you should be using 3 significant figures. Even if the temperature is given at 2 significant figures, you should still be using 3 significant figures. And the sort of the general reason for this is that if you think about the way thermometers work, most thermometers just don't go to 3 significant figures. But the things you do have to 3 significant figures is your you have your volume at 3 significant figures, and you have your thingy thing, and you have your pressure at 3 significant figures. So ignore the fact that your temperature is not at 3 significant figures. All right, so at this point, we have our number of moles of nitrogen, but we're actually looking at the minimum mass of sodium azide. That's what we want to be thinking of. So we can't just shove this number of moles into our mass formula yet, because we're not looking for the mass of nitrogen, we're looking for the mass of sodium azide. So those of you that had problems with the molar ratio last time, this is again another molar ratio calculation. So we're going to take the molar ratio for this one. So we have 3 moles of nitrogen for every 2 moles of sodium azide. So to get from the number of moles of nitrogen, I need to divide by 3, and then to get and then times by 2, which is the same as saying 2 over 3. So I have my 4.4 times my divide by 3 to get down to 1 mole from my nitrogen. So that's why the fraction is over 3. And then times by 2 to get to my 2 moles of my sodium azide. So that's why it's times by 2 over 3. So for that, I should have 2.93. So now that I have my number of moles of the thing I'm actually looking for the mass of, I can just shove into my mass is equal to number of moles times molar mass formula. And my molar mass of sodium azide is not given, but you guys should be able to work that out. So I'm not going to go through it. Is 6 to 5. And then we should be able to just, do the last bit. So we should have 2.93 times the molar mass, which is 65. And so the final answer to 3 significant figures should be 191 grams. Do you round intermediates? So I wouldn't in your calculator. So in your calculator, just leave them in their full form. But when you're writing it, you can round them. So the 4.4 is the number of moles of the nitrogen gas that we worked out using our ideal gas formula. And also with sort of intermediate numbers, moles wise. So lots of questions like this will have multiple answers allowed to make up for the fact that people will be rounding slightly differently. So you should have gotten 190.5 and then rounded up to 191. And you should also, so keep everything in your calculator the same rather than rounding. Yeah. that 1 gram though? Yeah, so when I was writing it down, I didn't keep all of the significant figures, but in your calculator, you should sort of leave the numbers in. And if you got 190, you probably be fine. Again, in the mark scheme, it has a set of numbers. Yeah, exactly. So in your calculator, when you're writing, just leave the full number of significant figures in there. Cool. So I'm going to finish up there and do like the usual wrapping up thing. Well done, everybody, for getting to the end. I really appreciate it's good general practice to not round your intermediates in your calculator. Yes. Lost my words. They like to disappear on me. Yes, I was saying thank you for sticking around. I hope that was useful. Always feedback is good. So if you guys have anything that you would like to do differently, or a different kind of like online session that you would like to see, always want to hear it. We like to know, and then we can produce all the content that is actually going to be useful for you guys, because that's what we do. So this part, if you haven't seen it before, or if you're just interested in seeing it again, yes, Jalaj, I will see you in 480 seconds. Our website has all sorts of things like this on it. So I'm going to talk you through those, and then I'm going to give you the code if you just happen to want to sign up. If not, and you've already seen this before and you're cool just sticking around on YouTube every Tuesday and Thursday, then I love to have you, and I'll see you then. But if you are interested in seeing what our website looks like, then I'm going to show you that right now. So our website, which is advertising our YouTube stuff, so you're already there. Yeah, if you buy the packages, yeah. So this is our website is a paid platform, because of course we actually have to like pay the people that produce all the content. So we've sort of done our best to sort of create everything we think A-level students might need. So if you are doing chemistry and you're on OCR, perhaps, we cover OCR, A, EdXL, and AQA as a general rule. So we have sort of like a bunch of content to sort of help you learn. So for example, if you wanted to have a look at acids, you would do first a diagnostic quiz, or you could skip it to sort of see what you know and what you don't know. And then depending on what you got, we suggest videos and parts of videos that you should watch to sort of like neaten up your knowledge. And then you do another quiz to sort of see how that's going. And then you can look at some exam questions run-throughs to sort of give you a better idea of how to do exam questions rather than just sort of general quiz questions. So that's sort of been our basic package, the cheapest one. So you still get a bunch of really cool stuff there. And then if you're in the pro package, we've got like a ton of exam questions that we've come up with that are like exam style questions for when you run out of past papers, because I know that happens a lot. And then you sort of do the question, and then you can have a look at the solution, which is sort of like sort of guided solution, so a little bit less confusing than a mark scheme, but as sort of rigorous. And then you can sort of mark yourself and sort of track your own progress, see how you're doing. So that's in our pro package. And then like the last package is the one with me in it. So you'll get to work with me all the time. Sort of like Monday to Thursday at the moment, while everybody's on lockdown, we have a bunch of web classes. So in about 6 minutes, I'm going to be doing a web class on halogenoalkanes, and I do a bunch of these every week. So you can see the schedules. We have a book club and personal statement writing workshops, and lots of different stuff every day. Yes, so my lovely colleagues just dropped the thing about the different packages you can buy and subscribe to. And there are also drop-in sessions every day, Monday to Thursday, where you can basically just ask me anything you're confused about, or we can go through an exam question or a topic that you are a bit like, oh no, this is hard. So yes, so that is what we do on our website. And we've tried really hard basically to just think of everything an A-level student might need and put it in a nice, neat little package with lots of sort of different prices for different things, so that Even if you have like no money to subscribe, you still have YouTube. And if you sort of have the cash, then you can sort of get a little bit more in terms of content. So that's what we've tried to do, try and make things as fair as possible. And I hope to see you on the platform if you want to join us. So go ahead and do that. And I will remember this time to give you the discount code, because I always forget, because you know, too many ideas in my head. I just have so many great ideas that I can't fit in normal things like remembering coupon codes. That's why, of course. But yes, thank you everybody who stuck around to the end. We appreciate you. Use your ideal gas 10 code. And I will see you on, what day is it today? Is it Tuesday? It is Tuesday. See, I even know what day it is. Tuesday. I will see you, no. I will see you on Thursday. Or if you're in my normal classes, I will see you in 4 minutes for the halogenoalkanes web class. But goodbye, lovely, lovely people.